Welcome to Monday Night Calculus. Good evening. I am your host, Curtis Brown. I am super excited to be joined here this evening with Tom, Dick, and Steve Kokoska here to start our spring set of videos and live casts here on the YouTube channel, Texas Instruments YouTube channel. I'm really excited to do this. Steve and Tom, thank you for joining us and having your expertise to be shared. I just want to put a couple of things up. First of all, welcome to everyone who's out there watching. Welcome students and teachers. Please make sure that you post all of your questions and comments and things in the chat box. I'll make sure that Steve and Tom get that information. Secondly, I would also like to just let you know that throughout the cast, I will put my email address in here. You can shoot me an email if you are looking to have the PD credit. I'll make sure to send you a link for that. As well, if you have downloaded the student documents, we'll be posting the teacher documents in the morning tomorrow up here on this very same YouTube link, so you can get into the description, download the student document, and then the teacher document has solutions and the essential knowledge and skills and lots of other really valuable information there. Steve puts a lot of time into putting that together for you. So look forward to this evening and for all the conversations. Steve, I think it's all yours.
Okay, thank you. However, you have to enable my screen sharing.
Oh, no.
Yes.
All right. I will make sure that you can do that.
Okay.
There we go.
All right. Looks good. Thank you very much, Curtis. All right. There we go. I think that's working. I'm going to make this a little bit bigger if I can. How's that? Okay. Can you see that all right?
That looks great.
Okay, thank you very much, Curtis. It's wonderful to be with both you and Tom again this semester. Just a reminder that we are doing things a little bit differently this semester. We're trying something a little bit different to our format. So about a week before each Monday night calculus session, we're posting some problems on very specific topics. And what we'll do on these Monday night sessions is that we will solve these problems. And hopefully this will raise a few questions from participants and maybe even some discussion of some conceptual ideas. So today, tonight's topic is the fundamental theorem of calculus, the most important idea in all of calculus and definite integrals. And what I'm going to try to do, Curtis, is a couple of problems that just illustrate the fundamental theorem of calculus, what we traditionally call part one. Then I'm going to kind of take a step back a little bit, and I'm going to do a problem that I really like, that I think sort of motivates the conclusion of the fundamental theorem of calculus part one. Then we'll do some problems that illustrate the fundamental theorem of calculus part two, and I'm not even going to sneak in a BC problem in there if I can. And then we'll do a couple of not unusual problems, but some problems that might involve net accumulation or net change, and some unusual problems that you might see on an AP calculus exam sometime in the near future. So here we go. Let's see if we can use the fundamental theorem of calculus to find the derivative of each of these functions. So what I've done is I have defined a function f of x this way. That was the original problem. And we want to find the derivative of that function. Now, we all remember the fundamental theorem of calculus, part one, is defined so that the constant is down here at the lower bound and the variable x is up here in the upper bound. So we can't apply it the way that this function f is written. However, we can switch the bounds. And when we do that, we get a negative sign out here. And the reason that we can do that is because I'll just sneak a word in off to the side. That's a property of definite integrals, which is if we reverse the bounds, we have to put a negative sign out there in front of the definite integral. Well, now we'll just carry down this negative sign. And here is just a very straightforward application of the fundamental theorem of calculus part one. If we want the derivative of that function defined as a definite integral, we simply plug in x everywhere that we see a t here. And so there's our derivative. Pretty straightforward. Might see a question like this on multiple choice. Uses a property of definite integrals. So each of these next two problems takes this idea of the FTC part one a little bit further. Let's look at part B. So here we've got a definite integral, a function defined as a definite integral from 1 to the square root of x. Well, one good thing right away is that the constant 1 is down there at the lower bound. However, up here in the upper bound, we actually have a function of x, not just plain old x, but a function of x. Now, I'm not going to go through this one in great detail, but in order to find the derivative of this function, we do actually have to use the chain rule. And I'll just sneak a little bit off to the side. If you want to write this out in a little bit more gory detail, you would, of course, let u equal to the square root of x, find du, and go from there. So what this amounts to, the short way of thinking about this is everywhere we see a t, we've got to plug in a square root of x, and then we've got to multiply by the derivative of that function up top here as the upper bound. So don't let me make a mistake on this one, Curtis. I plugged in the square root of x. Let's see, I think when I square that, I get an x. When I raise that to the 8th power, I think I get an x to the 4th. The derivative of this function, well, just the power rule, 1/2 x to the minus 1/2. And I think I did a little bit of simplification here. There's the 2 in the denominator. And I think I did a little cancellation with those two expressions for x. So again, another kind of straightforward application of the fundamental theorem of calculus part 1 and the chain rule. And let's take a look at one more here. This is kind of a cool problem because, well, it has functions of x in both the lower and the upper bound. And so what do you do here? And the trick is to use another property of definite integrals, and that is to introduce a constant. Often we use 0, but just for a little variety, I used 1 here. And I can split this definite integral up into two separate definite integrals. So I can go from the log of x to 1 plus 1 to x squared. So that again is a property of definite integrals and allows me to split this up into two separate definite integrals. Now, I know what to do with this one. I just did that in part B. And actually, I know what to do with this one too, because I kind of did that in part A. I need to use another property, that same property of definite integrals, where I reverse the bounds and put a negative sign out in front. And in both cases, I'm going to have to use the chain rule. So here, I flip the bounds. Here, I kept the bounds the same so that I have the constant as the lower bound. And now I'll take the derivative of each one of those using the fundamental theorem of calculus part 1 and the chain rule. So kind of weird looking, but wherever I see a t here, I'm going to plug in a log of x. So that looks good. Multiplied by the derivative of the log of x, that's the chain rule, the derivative of the inner function. Second definite integral, wherever I see a t, I plug in an x squared. Multiplied by the derivative of x squared. And let's see, don't let me make a mistake here, Curtis. I think I did this right. The derivative of the log of x, 1 over x, there's my x in the denominator. There's my negative sign. I didn't lose that. Let's see, derivative of x squared is just 2x. Just to make it look a little prettier, I wrote that out in front. And I don't know if there's any simplification there, perhaps. I don't know, maybe factor out an x from the denominator, but I think I would just leave it like that. Pretty cool. Tom, do you have some technology you want to look at here?
Sure, Steve, that'd be great.
Okay, I'm going to stop sharing. And there you are.
Okay. Let's see if I can get my screen shared here. Hopefully you're looking at a TI-84 screen here. Does that look okay to you guys?
Looks good.
Yeah, that looks really nice.
Great. So I just wanted to, well, get on a little bit of soapbox here, but the one thing I like to do with differentiation in general with my students is have them check their answers visually and numerically. So when they're doing a derivative by hand, I like them to, for example, check it against the numeric derivative. And you could graph both your own one that you found and the numeric derivative and see if they match up. Or visually, what I like even better is to graph the original function and then have them graph their derivative and look and see if it makes sense from a slope point of view. Is their derivative telling them the slope of the original function at each point? Now, with these kinds of functions that Steve's been showing, using that fundamental theorem of calculus to create a definite integral function, you might think that those are out of bounds for graphing, but they're not at all. We can actually graph those just very easily on the 84. And that's what I wanted to demonstrate. But I did want to show a feature that you might want to take advantage of. So I'm going to go to my y equals menu. And you can see there's something complicated in y1. We'll come back to that later, but I'll go down here to y3. And I'm going to look at that first example that Steve had. And he was integrating from x to 2, this t cubed sine square root of t. Now, if you have a late enough version of the 84, you go to your math menu and pull up the fn int down there at number 9, you come up with this really nice, it's called the math print. So it looks just like an integral, put in your lower and upper limits and all that. But one issue of that is we're going to be asking the calculator to graph a value for each pixel across the screen. It's going to be doing a separate definite integral. And this was a fairly complicated integram. So that can really slow things down. So what I'm going to do is actually clear that off and go to mode. And you see up there at the very top says math print and classic. I'm actually going to change it to classic mode. Huh. And what that means is when I go to y equals and I bring, oh, you can see that y1 really changed its look. Mm-hmm. I'll go down to y3 again. And I'm going to bring up the math menu. And this time when I do fn int, it actually comes up with that name for that function. And what we're going to do is just type in, first of all, our integram. So I'm going to do alpha t cubed times the sine of t, or excuse me, sine of square root of t. Mm-hmm. Yeah. Caught myself there. And then we're going to put in a comma. We put in the variable of integration, which is t. And now we put in the bounds on our integral. Now this one, I think it started at x, and then went up to 2. Mm-hmm. Now, usually this is where I put the final parenthesis and start to graph. But as I warned you, you can try that. It might graph painfully slow because you're really asking it to compute a lot. So what I'm going to do is add one more thing, and that's going to be a tolerance. I'm going to put in 0.05. And what that means is it's only going to try to calculate to the nearest 500ths. And the reason I picked 500ths is on a zoom decimal screen, our pixels are worth 0.1. So that should get us to the nearest pixel. But it'll do it much faster because we're not asking it to compute so exactly. If you were doing a definite integral for just at one specific value on your calculator screen, you'd like it to be accurate to lots more decimal places. But for visual purposes, we're going to give this a shot. So let me go ahead and graph this and see what we come up with. Here it comes. And you can see, even with that tolerance, it's not graphing as fast as just a plain old function, these definite integral functions. So you see that graph. And what I'm wondering is that a reasonable or if I calculated a derivative and then graphed it, would this look reasonable? Now, on the problem that Steve had, one of the most common mistakes would be to forget that you have to flip those bounds, right? So you might just think, oh, the derivative's just put in the x in for t. So I'm going to go ahead and do that. Graph x cubed times the sine of the square root of x. And let's graph that. Okay, now visually, I can tell there's something drastically wrong. It may not jump out at you, but the thing is, my derivative is positive. But my original function is going down as I move from left to right. I should be seeing a negative derivative here. And that's a clue to me, oh, I forgot something. I made a mistake. And in fact, if we go back to y equals, and we just edit, insert a negative sign for our y4, and then regraph, here comes our original definite integral function. And then we should see the derivative, which this time is the one that Steve came up with. There it is. And that looks a lot better. It's very, very flat up here. So my derivative should be close to 0. And then my graph is going down and it's getting steeper and steeper in the down direction. So my derivative graph should be getting more and more negative. So now that I'm more reassured, it's not a surefire check, but it is at least a reality check on, does this make sense? And for these definite integral functions, I'm finding it really helps you catch those kinds of errors. For example, I think I've used enough time here, Steve. I don't want you to have plenty of time, but on that next problem that you did with the square root of x up in the integral bound, the most common mistake is people forget to use the chain rule. And this would be another way to catch that kind of mistake. If you graphed it without that chain rule in there, you would be looking at it and say, wait, that's just not making sense. So it's really useful. And also I find this visually checking the derivative against the original graph is always, can't get enough of that kind of exercise to get that visual sense.
Tom, before you leave this page, I have one more question probably for Curtis. I'll play the devil's advocate here. I don't understand why there is no part of the graph to the left there of the y-axis. So I wonder if any of our participants could tell us that. I initially might incorrectly think that it had something to do with what you entered in fint, but I don't think that's it. I wonder why there's nothing over there.
Wow.
That is a really good question.
Just to get you thinking a little on a Monday night.
I'm going to watch the chat here and I'll tell you what your participants say. I do want to point out that Mark Crowley said that he's really enjoying watching you on TV tonight. He's casting you guys on the large screen tonight. And his daughter is joining him for that, which is great. We've also had some comments of folks using using your work in their classroom as students.
Cool.
This week, which is really good. Good to see that stuff.
Right,
and Wanda Burns commented and just clarified for us the square root of t is really the reason we have that limitation on the domain. Wanted to pass that on to the chat folks and let them be the ones to come up with that.
Very good. Yeah.
See if anyone was out there listening.
Very good. All right, Tom, should I try number 2?
Sure, I'll stop the share and turn it back over to you.
Here we go. Thank you very much. All right, let me try to make this full screen again. The technology seems to be working, so there we go. So Curtis, this is one of my favorite problems that I like to do in class, one very similar to this. Unfortunately, I don't think my students share in my enthusiasm for this, but I think this is a really cool idea, and it helps us sort of discover, see maybe a little bit some empirical evidence of why the fundamental theorem of calculus part 1 is actually true. So here's the graph of a function shown up above here, and it's made up of a couple of line segments, and you can probably see a quarter circle in there. I wanted to add that in there because there was actually a question that involved something like this on the AP exam a few years ago, and students had a difficult time with it. So I'm going to define now this function g, which is a definite integral from 0 to x f of t dt. And what I'd like to do is to use this graph, use an interpretation of this definite integral to see if I can evaluate g for these integer values. And then when I'm done with all that, I'm going to try to put it all together. I'm going to cheat a little bit with technology, but I'm going to put it all together and try to get a rough graph of this function g. So here we go. Bear with me, Curtis. I'm going to scribble a little bit on the right-hand side if I can where needed, and I might need a couple of answers here. G of 0, well, I just plug in x equals 0 up there as the upper bound. That's an easy one. That's a property of definite integrals. I don't even have to look at the graph. I know the answer is 0. What's g of 1? Well, I plug in 1 on the upper bound here, and what I need to do is to remember that we can interpret this definite integral as the area underneath the curve, and we have to worry a little bit about whether the function dips down below the x-axis. But let's see, if we go to the graph here, we just have to find the area underneath the curve between 0 and 1, and that's pretty easy. That's just a right triangle, and I'll add in a little bit more off to the side. That's just 1/2 times the base times the height for a 1/2. So we're on our way here. How do I find g of 2? Well, okay, I plug in a 2 up there, and you're absolutely right. What I probably should have done here was rewrite this as the integral from 0 to 1 of f of t dt plus the integral from 1 to 2 of f of t dt, because I already know this one, and then I can use this idea of finding the area under the curve from 1 to 2. So this amounts to finding all of this area plus all of that area. Over here, let's see, I have a square down here, so that's 1. And I have another part of a triangle up here, which is 1/2. So there's 3 halves in there, plus that 1/2 for a 2. So I'm making progress. 0 to 3, well, let's see. I know this area, 0 to 2. And here's 2 more units, so that's easy. That's just a 2 plus 2 for a 4. I'm making good progress. How do I find the area from 0 to 4? Well, let's see. I know this area. That's 4. And this area, well, that's just another 2 units. So now I've got 6. And now things get a little trickier. I'm going to go to the next page on this one. How do I find g of 5? Well, actually, when I do this, I'm going to do a little bit of approximation because I'm not sure exactly how to find this area yet. So I've got to find the area from 0 to 4, and then I've got to add this little area in there. Well, I know from 0 to 4, I have 6 units. And what I'm going to do is approximate a little bit, and that'll be good for now. I took a little bit of a look at that area under the curve, and I figured, you know what? That's about 0.75 of one of those squares. So I'm going to guess that this area is about 6.75. And that's a pretty good approximation. And it isn't going to really affect anything too much here. But let's see, when I go 0 to 6, I can actually be a little bit more exact. I know the area from 0 to 4. What do we have there? That was 6. And this area under here, I think I can get, let's see, what can I do here? Well, let's see, I know this total area, right? I know that total area, that's a big square. That's 2 times 2, that's 4. And then what I need to do is to subtract that area over there to get the remaining area. And that's just the area of a quarter circle with a radius of 2. So it's 1/4 pi r squared. And if I did everything correctly here, that becomes a 10 minus pi, and I'm making really good progress. So 0 to 7, saving a little bit of time here. What do I need to do now? I take the total area from 0 to 6, there it is. But this region is below the x-axis, so I have to subtract that off. That's the area of a triangle, but again, it's below the x-axis, so I have to subtract off a 1/2. There's my exact value for g of 7. G of 8, well, okay, I've got a little bit more area down there that I have to subtract. I got an 8 minus pi. And g of 9, I've got to subtract off even a little bit more. And I've got 11/2 minus pi. So that's a nice problem that I think your students could actually do in groups. We've got all these values of g, and now what I would ask my students to do is to graph both f and g on the same coordinate axes, and here they are. So this is a graph of f that was given to you. I just don't have in all the little grid lines. And there's a graph of g of x. If you're watching in color on a big screen TV, that's in green. and now you want to ask your students, you'd like to ask them, I think, can you describe the relationship between the graph of f and the graph of g?
So Mark actually commented that his graph looked pretty good up until about somewhere between g of 4 and g of 5. It started to get to looking a little bit rough. It's hard to draw those
it is indeed
exact responses.
Yes, it is. It is indeed. It is a little difficult. Here's what I got when I connected the dots. And as Tom was just mentioning a little while ago, well, look, what's the relationship here? What would your students see? I hope they would see here that as g is increasing, the graph of f is positive. Right here, where the graph of g is almost flat, f is almost 0. And here from 6 on out, where g is decreasing, the graph of f is negative. And so if they look at that and stare at that long enough, that might suggest that there is some sort of a relationship here. That is that g prime of x is equal to f of x. And that, I think, is kind of cool. Tom, I apologize. Do you have a technology application here for this one?
He does, but he's on mute.
Yes, I'm on mute. Sorry.
Okay. Right.
Yeah, I think I have a couple of things I could show here.
All right, there you are, sir.
All right. Okay, so I'm going to share my 84 again. And the problem that Steve just illustrated, I think for the last 20 years at least, there has been some problems similar to that in flavor on the AP free response question, where you're given a graphic function. It's shown graphically with no formula, and you're asked to do, you're either told it's the derivative of another function, or you're asked to do something with a definite integral function based on that. Both of those amounting to being able to interpret the fundamental theorem of calculus correctly. These problems are pretty much guaranteed to be on the non-calculator part of the exam. But when you're doing these with your students, you may want to employ technology just to do a check. And for example, Steve showed a kind of a graphical plot of connecting the dots that he came up, each one with a calculation he'd done by hand. Some folks wonder about, can you do like a split defined function on the calculator? And the answer is yes. It's not hard to do at all. I just wanted to illustrate that here quickly. So I'm going to go to the y equals menu. And in Y1, what I've done is I've actually gone ahead and put in the formula for that piecewise. It's a kind of a combination of linear, constant, and the circle. For a circle. But that's the done deal. If you're entering let's say I just wanted to do the first two pieces of that graph. Let me use Y2 as an illustration. You go to your math menu and scroll down. Quite a ways. Oh, overshot. There it is, piecewise. That's exactly the thing we want. And it asks, well, how many pieces do we want? I'm going to just do the first two as an illustration. So I'm going to say 2 pieces. And then we'll say, OK. And it gives me a little template that I can enter those first 2 pieces. Now, I think the function, it looked like it was just going up on a 45-degree slope there. I think it's basically y equals x.
Mhm.
And that was good for 0 up to 2.
Mhm.
And so here we'll go to the test menu, and it says conditions up there. And you can see we've got lots of selections here. I'm going to go down to number 7. And something I should have done first is put in the beginning value. So let me arrow over there. I'm going to insert 0. And so I've got 0 less than or equal to x, and x is less than 2. Okay. And that's the first piece. The next piece, I think it's just the constant 2.
Mhm.
And let's see, this time I won't make that same mistake. I know I want to start at 2. And now I'll do the test conditions. And I'll go use actually number 5. Because I'm going to end this at 4.
Okay.
Remember, I'm just doing the first 2 pieces of that graph. And there we go. And I think I'm ready to try to graph it. There we go. Got the piecewise one there, and it looks really good. Now I'm going to go back to y equals and turn off y2. And the toughest piece of this was that circle piece, getting it correct. Let's see if I was able to get that all right. Let me try my y1. And hopefully we get something that looks like, yeah, I think we're okay.
Pretty good.
Looks all right. And then finally, can we do a definite integral function for this? Well, that's what I've got down there in y3. And I just wanted to, in case people didn't believe me before, I'm going to highlight that, and let's go ahead and graph it. And here it comes, but it is slow. And it's going to get slower when it hits. Oh, it's moving like molasses. You know, I'm getting impatient, so I'm going to hit on to break out of that. And then I'm going to go to my mode and change math print to classic. And then when I go back to the y equals menu, now everything is back into that kind of line form. You see the piecewise thing is really, it's all in one long line. It wraps around over and over. But now when I go down to y3, that's where I had my integral function.
Mhm.
I'm going to insert a tolerance of, I'm going to put in 0.1. That should make it graph a lot faster. So let's try graphing again and see what we get. Okay. And I hope it doesn't make me eat my words. I hope we get a reasonable graph here. It does seem to be moving faster than it was before.
Yes.
Tom, you could also grab the mode setting or sorry, the formats. Sorry, the window. Man, if I keep pushing buttons, I'll finally get there. If you get to the window key, you can go into XRes and change that resolution to like every 3rd pixel or something like that as well. That would increase the speed.
Okay.
Derivative too.
Yeah, that's one I've often used, though I often find myself forgetting then to change it back to the original.
That's true. That's true. You got to be.
This tolerance thing
aware.
is kind of a nice thing. Yeah,
I
didn't have my Y max set up quite high enough, so there's part of the graph we can't see. And you see, even with the 0.1, it's still moving slow. But I think we're getting a graph pretty similar to Steve's.
Yeah, looks
So
like
Tom,
it's very similar.
Tom, may I ask, with setting the tolerance, is it actually computing the definite integral for every pixel versus
absolutely. It's just not
doing
it quite as accurately, and so it's saving a little bit of computational time.
And that's different from changing the resolution, which finds the definite integral at every like 3rd or 4th pixel.
Exactly. So it's doing the same accuracy as normal, but it's plotting fewer points.
Gotcha.
And in fact, Steve, what you did, you only did a point for every integer. So
correct.
but you did. Yeah. So you really sped up the resolution.
Gotcha.
All right.
Okay.
Okay. Well, that's what I got. I'll go ahead and stop the share and turn it back over to you,
Okay.
Steve.
All righty. Thank you. All right. Here we go. So, Curtis, what I'm going to do now is shift a little bit here, and we're going to take a look at some problems that involve the fundamental theorem of calculus part 2. To the teachers out there, if you've covered this, I think these 5 problems are a nice review for tomorrow morning. At least one of them in here is for your BC students, but the other 4 are good. And I did add in part here, in parentheses, you might think a little bit about the geometric interpretation of part A, but then after I did that, I wanted to look at the geometric interpretation of all of them. So I think that's a good thing to do here, to use the calculator to take a look at what these definite integrals really mean in the coordinate plane. So, all right, I'm going to take a look at all of these. Let's see what we can do with part A here as I arrow down. So what's the fundamental theorem of calculus traditionally part 2 tell us? It says, well, look, if we have a definite integral like this and we can find an antiderivative, then all we need to do is to evaluate that antiderivative at the upper bound and the lower bound and then subtract. And that's a heck of a lot easier than trying to form a Riemann sum and trying to simplify that and trying to take a look at a limit as n goes off to infinity. This makes our life a lot easier. So, okay, an antiderivative of the sine of x is minus the cosine of x. Yes, you can bring the minus sign out here. There's a parentheses here in blue. I'm going to plug in the upper bound pi, the lower bound 0, and I'm going to do a little bit of simplification here. And son of again, I get a +2. And I always find this kind of a problem, this kind of an answer, absolutely amazing, because here I am integrating a transcendental function, and the exact area underneath that curve from 0 to pi is 2. I find that absolutely remarkable and yet true. All right, let's take a look at B. Suppose I want to find the definite integral from 0 to 3 of e to the minus x. Well, okay, this is really a very simple U substitution problem. And actually, Curtis, in our next Monday night calculus session, we'll be looking at U substitutions in much more detail. Most of your students
I'll go review my notes.
Most of your students are so good at this that they can just look at this and know what the answer is, know that they need a negative sign in here, know that the derivative of that inner function minus x is a -1. So there's the antiderivative, and I need to evaluate that at the upper bound 3 and the lower bound 0 and subtract. And I think I did that. I got an exact answer of 1 minus 1 over e cubed, and I got an approximation of 0.950. Some people don't like this, that we write an equal sign here. We know that those two values, or pardon me, those two expressions are not exactly equal. But just for simplicity in AP calculus, where we report 3 digits to the right of the decimal, we usually use an equal sign there. I just wanted to say something about that because students will not be penalized if they put an approximation symbol in there. And in general, we use an equal sign. And here's a geometric interpretation of this. We know what y equal e to the minus x looks like. It gets closer and closer to 0 as x increases without bound. It starts up here at the point 0, 1, and the exact area underneath that curve is 1 minus 1 over e cubed. That function e to the minus x is entirely above the x-axis, and so we can think of this as area underneath the curve. Here's another good one, I think. Where'd it go? Here it is. 0 to 3, x e to the minus x squared. Well, again, this is a U substitution problem. I've got to find an antiderivative here, so I'm going to let u be equal to minus x squared. You'll get a little bit of a flavor here, a little bit of a taste of how I like to do these problems. I've got to find du. I take the derivative on the right-hand side. I've got a minus 2x. Don't forget the dx in there. And my next step is always to solve for dx. I do that with an eye towards bringing everything from x, everything in the x world into the u world. So I want to transform this expression from something that's kind of difficult in x to an integral that is a little bit easier in U. Well, when I do this in a problem like this, with this definite integral, I've got to drag along the bounds also. So I'm bringing all this integral across this bridge into the U world. I've got to drag along those bounds also. So what happens when x is equal to 0? Well, I just plug in an x equals 0 over there. Well, I get u equals 0. When x is equal to 3, well, let's see, it's minus 3 squared, it's minus 9. Whoops, there's the pen. So, okay, I'm going to bring everything from x's into everything in u's. The bounds become 0 to minus 9. Notice here that in some sense, the order of these bounds has changed. In other words, the smaller numbers now up top. That's okay. It doesn't bother us. We can still evaluate this definite integral. I'm going to leave the x alone out front. I've got an e to the u because u is equal to minus x squared. And then I'm going to substitute in for dx. This step is okay for me. It's sort of this intermediate step. It's sort of, I am on this bridge walking from the x world to the u world. I'm going to cancel everything out that I can. The x's go, and the minus 1/2 comes out in front. And son of a gun, I'm lucky here. I made a good substitution. We'll talk more about this in a couple of weeks. I'm left with an integral in u that I can evaluate. And so a question, a sort of a rhetorical question, Curtis will leave out there is, what happens if you make a substitution, u is equal to some function of x, and you walk across this bridge and you end up with a function that is in both x's and u's? What do? We'll leave that as sort of a question outstanding, and maybe we'll get to that in a couple of weeks. All right, I need an antiderivative of e to the u. That's easy. That's just e to the u. And now notice here, I'm in the u world and I've dragged along the right bounds. So there is no need here at all to go back into x's. I understand the desire to do that on the part of some students, but there's no need to do that at all. I can evaluate this expression at the upper bound and the lower bound 0. And let's see, did I do that right? There's an e to the 0 in there, a 1, and there's a minus sign there. That's why it's a plus 1. 1 minus e to the minus. Hey, I'm a little confused here. That expression actually looks positive. I was worried about this because I've got a negative sign out front. I've got a negative 9, which is the smaller number up top. Let's take a look at this geometrically. Well, if I graph the original function, x e to the minus x squared, oh, now I feel a little bit better about this. This is always above the x-axis. In fact, x is positive to the right of 0. E to the minus x squared is positive. And so this function is graphed always above the x-axis. And indeed, the area here is this expression, which is indeed a positive number. I feel a little bit better about that one. Good.
Steve, I'm not always sure whether you're actually panicked about your mathematics there, or if that was if you were just playing that up just a minute. All of a sudden I was thinking, oh man, I need to really pay attention and check his signs real quick.
Oh, I'd like to think we know what we're doing here, Curtis. Let's try this one.
Well, at least two of us do.
Let's take a look at this one. Minus 3 to 0, x squared e to the x. Okay, so this is a BC problem. So I'll write that off to the side here. So if you've got some BC students tomorrow morning, you can.
I know you can't see the chat, Steve, but Mark just said if you make the problem all about you don't have to worry about going back to your x.
Well, I like that. All right, how do you do this one? How do you find an antiderivative? What I'm going to do in this problem is I'm actually going to ignore the bounds for a minute and just solve this indefinite integral. And then when I'm all done, I'll put the bounds back in. So what I've got to do here actually is use two applications of integration by parts. And I won't go through this in gory detail. Remember, I think, Curtis, you said that we will be posting all these solutions. But I do need to use two applications of integration by parts. When I'm all done, I think I've got an expression like that. And so what I did here is now I went back to my original expression, my original definite integral. There's an antiderivative, and I have to evaluate that at the upper bound and the lower bound. Plugging in the upper bound isn't bad because, let's see, that's 0, that's 0. So I just have a 2 times e to the 0 or 2. Plugging in a -3. I think I did everything okay there, and I did a little bit of simplification. And I think I've got 2 minus 17 over e cubed. I'm going to draw a graph of this one too. I like this graph. This is from -3 to 0, x squared e to the x. Well, e to the x is always positive, and even to the left of 0, x squared is positive. So again, we can interpret this as area under the graph. Curtis, I wanted to take just an extra second here, an extra minute, and write something on the side here. I've seen this more and more on the AP exam, and I don't teach this, but I guess a number of people do. There's a sneaky way here for BC students actually to get this antiderivative. If they're trying to find an antiderivative of x squared e to the x, and I won't get this right. I know Mark Corrali and Wanda will know this much better than me. But I think of this as a tabular method, and I guess it only works if you have a polynomial times a, I'm going to say transcendental function there, like an exponential function, like a sine function, a cosine function, tangent, arctangent, something like that. There may be more strict rules and guidelines on that, but I'm pretty sure it works here. And the way that we do that is we draw a table and we put in x squared over here. And what we're going to do is work our way down, taking derivatives. And we're going to start with e to the x here, and we're going to work our way down, I believe, taking antiderivatives. So the derivative here is 2x, the derivative here is 2, and we stop when we get a constant. An antiderivative here is easy, antiderivative here is easy. And I think Mark will have to help me on this one, but I think we have to add a plus, minus, like that. I think we have to alternate signs. Seems like it's almost more complicated than doing the integration by parts, but actually helps. And now what I think we do is we multiply across and add everything together. And I think if you do that, you'll see that I got this antiderivative right here. So that's kind of a sneaky way to do integration by parts when you have a special case here of a polynomial, what I'll say times transcendental. And I'm sure someone has written this up much better than I just described. But I've seen that more and more, as I'm sure Tom has on the AP exams on the BC part. All right, I'm going to do one more, Curtis. I like this one a lot.
Mark said he doesn't teach it for all the reasons you spoke up about.
Well, I don't.
However,
yes,
you got it right.
Okay. So this is a good one to give your students to think about assumptions, to think about what must be true before you can actually use the fundamental theorem of calculus part 2. Let's take a look at the integral of -2 to 2, 1 over x squared. Sort of a knee-jerk reaction as well. I'll find an antiderivative, and I'll just evaluate it at the upper bound and the lower bound here. Well, I've got a red not equal in there, but I put an antiderivative in there. Can somebody tell me why the fundamental theorem of calculus part 2 does not apply here? Why doesn't it work here? Why?
Well, I've got a stab at it. That's not continuous.
Beautiful. That indeed is it. This function, this integrand is not continuous. And so we can't apply the fundamental theorem of calculus part 2. And in fact, if you did this and even went a little bit farther, don't let me make a mistake. There's the minus sign out in front. If I plug in the upper bound, I get a 1/2. Subtract off what I get when I plug in the lower bound. I think that's a -1/2. And Curtis, did I do this correctly here? I get a 1/2 plus a 1/2 for a 1 on the inside. And I'd get a -1 is my answer. I know that can't be the right answer by looking at this graph. And why is that?
Well, I mean, everything's above the x-axis.
Everything is above the x-axis, exactly. So I know that can't be the right answer. I know that I've done something wrong. Fantastic.
Wanda chimed in and said that x can't be 0. So that, again, that just
Yep.
reiterates
The domain. Yeah,
we
thinking
don't
about
have-
the domain.
yeah, we have domain restrictions. We don't have continuous domain.
Very good. Okay, Tom, is it okay? Can I take a look at number 4 here?
Sure. Please
Okay.
go ahead.
Okay. So this one now, these last couple of problems, Curtis, is sort of, we put everything together. And you might not be quite sure what part of the fundamental theorem of calculus to use, what other idea or concept we need, kind of a neat AP, I think, calculus exam type question. So here's a function g, defined as a definite integral. I like that I see just an x up there. I like that I see a constant 0 as the lower bound. But wait a minute, this says find the intervals on which g is concave down. So I'm going to think out loud a little bit. How do I do this? How do I figure out where the heck is g going to be concave down? Well, I guess that what I'm going to have to do is to find the second derivative. I'm going to have to find g double prime. And I'm going to have to find where g double prime is negative. Okay, so that's a problem that you probably did at the beginning of the semester here when you learned how to take derivatives and you learned the relationship between derivatives and graphs. But now we know a little bit more here, and we're applying that idea and using the fundamental theorem of calculus. Cool. Well, let's see. I found the first derivative pretty easily. That's a piece of cake. I just plug in x everywhere I see a t. But now what do you do to find g double prime? Well, unfortunately, I guess I've got to use the quotient rule. And I'll save you a little bit of time. I think I did that all correctly. Denominator up, derivative of the numerator, minus the numerator, derivative of the denominator, a little bit of simplification, and even more simplification. So what I did with that circled expression, Curtis, I factored completely both the numerator and the denominator. And I did that looking ahead here because in my mind, what I'm going to be looking at eventually is a sign chart. And then for the AP exam, I might have to completely interpret that sign chart. Well, let's see. Where is that second derivative 0? Since I've got it completely factored, I know that it's 0 at -4. I know that it's 0 at 0. That divides up my domain here, my x-axis, gives me some intervals to take a look at. And now what I'm going to do is to plug in values and try to determine the sign of g double prime. We've talked a little bit about this before, Curtis. Some people like to actually take specific values of x and plug them in. I guess my way of doing this is to sort of think in general. So I'm going to look at the denominator and I can see that that's something squared. So I know that's always positive. So I know the sign of the second derivative is completely determined by the numerator. So let's take a negative number way, way less than -4. Both of these expressions are negative. I multiply them together. I get a positive value. I cross over -4. Take a value between -4 and 0. This expression is now positive. That's still negative. I multiply them, it's negative. Cross over 0, both expressions are positive. Multiply them, they're positive. What does that tell me? Well, I know that the graph of g would be concave up here, concave down here, concave up here. I'm not asking about inflection points, although we could. And that tells me that the graph of g is concave down on the interval -4 to 0. You'll notice that I used open intervals here. On the AP calculus exam, we don't take off for that as long as there is no contradiction. For example, is the function undefined there? And on the AP exam, I'd probably need some sort of justification here by saying something like, well, the graph of g is concave down on this interval because g double prime is negative on that interval. That's a neat problem, I think, one that one might see on an AP calculus exam sometime in the near future. Tom, okay to do the next one?
Yes, sir.
Okay. This one is a little bit different here. Oh, I wish I could hide a little bit of that. Here's a function, or here's an expression, and it says find a function f and a number a so that that expression is true for all x greater than 0. Well, that's kind of a crazy looking expression. What do we do there? Well, this is a good example, I think, of something that Tom and I have talked an awful lot about, and that is problem solving. How do you solve that problem? What do you do? What does this lead you to as you think about? How do you get it back to something you know? What do you see in here? Well, okay, I see this expression, and at least I know I can take the derivative of that. It's kind of set up for that. It's screaming out at you, the fundamental theorem of calculus part 1. And so what I'm going to do is take the derivative of both sides of this equation. Now, there's a little bit going on in the background that we're kind of glossing over, and that is if I have two expressions that are equal, can I take their derivative and are their derivatives equal? And the truth is yes, okay? But I'm not going to prove anything, but I might ask you to think a little bit about that. You might even think a little bit about that geometrically and why that's true. So on the left-hand side, I take the derivative term by term. The derivative of 6 is 0. The derivative of this expression is the FTC part 1. So it's f of x divided by x squared. And on the right-hand side, well, this is really what? 2x to the 1/2. So I can take the derivative of that using the power rule. 2 times 1/2 x to the minus 1/2. And now I'm going to do a little bit of simplification here. Hey, this is looking pretty good. I'm going to bring the x squared to the right-hand side. The 2's cancel. A little bit of simplification. Now I know exactly what f of x is. It's x to the 3/2. I'm halfway home. Now, how do I find a number a that makes that true? Well, let's see. I guess another thing that's screaming out at me is, well, how the heck do I get rid of that expression? Well, if I went from a to a, we know that that definite integral would have to be 0. So that's what I'm going to do. Every place I see an x, I'm going to plug in an a. That definite integral is now 0. I've got a 2 square roots of a, on the right-hand side. And let's see, did I solve that correctly? The square root of a is equal to 3. Square both sides. A is equal to 9. That's a nice expression. You should try that one tomorrow morning, I think, with your calculus class. That's a nice one. And Curtis, I've got time for one more. I'm going to do this one if I can. I really like this next one. If you think you really know the fundamental theorem of calculus, part 1, try this one. Have your students try this one tomorrow morning. If f of x is equal to 0g of x, so now what happens is this expression up here as the upper bound is a general sort of expression g of x. And I'm going to define g of x as son of a gun, another definite integral with a cosine of x up there. And what I want to do is find f prime of pi over 2. Yikes. Holy Toledo.
Yeah, this is a good challenge problem.
I like this one. I like this one. So the first thing I'm going to do is, well, I guess when I look at this, my intuition says I'm going to find an expression for f prime first because, well, I got to find f prime of pi over 2. That's not so bad. Every place I see a t, I plug in a g of x, and don't forget the chain rule on the end there. There's a g prime of x. So this says to me, well, I've got to find g prime of x, and I'm going to have to find g of pi over 2, right? Because, well, I've got to find f prime of pi over 2. All right. What's g prime of x? Well, now I'm looking at this. This is the FTC part 2. Every place I see a t, I'm going to plug in a cosine of x. This looks kind of weird, but it's correct. Sine of the cosine squared of x. There's the chain rule, derivative of the cosine minus sine of x. And all I did here was a little bit of simplification. That's all, to write it a little bit prettier. All right, I think I'm ready to do some evaluation here. G of pi over 2, where is that? G of pi over 2. So this is 0 to the cosine of pi over 2. Wait a minute. What's the cosine of pi over 2? That's 0. So this just simplifies to 0 to 0. That's easy. That's 0. Good. What's g prime of pi over 2? Well, I've got g prime here. I'm going to plug in a pi over 2 minus sine of pi over 2, 1 plus sine of cosine squared of pi over 2. Holy Toledo. Sine of pi over 2, 1. Cosine squared, cosine of pi over 2, 0. So square that. Sine of 0 is 0. That's just minus 1. Yikes. All right. I'm looking back up here. I'm going to put all of this together. F prime of pi over 2, 1 divided by 1, square root of 1 plus g of pi over 2 squared, which is 0 squared, times g prime pi over 2, which is minus 1. That whole thing is equal to minus 1. That's a great question. Try that one tomorrow morning. And we have one more, which we'll post the answers to, Curtis. This is kind of an applied problem. This problem is kind of neat. It involves rate in, rate out. It involves the fundamental theorem of calculus, and it is a calculator active problem. That's kind of a nice one, a nice practice problem for your students also. So
I
thanks,
just like
Curtis.
a good electronics problem there to finish things off, a little
I like that one.
battery issues. So that's good.
Very good. Thank you, Curtis.
Well, Steve, Tom, really appreciate it. Great way to kick off 2023. This has been a good session. Like I said, we will get these problems and their solutions posted in this YouTube link. So if you open up the description down here at the bottom, and this is the plan for the spring, we're going to make sure that we have the student and teacher documents in here in those descriptions as we go. The student document up first, and then the teacher document on the day of the go live or the day after, depending on when we get it ready to go. So again, if you want to, I'll put my email in the chat, and you guys can email me if you would like the professional development certificates. You can email me for a link to get those. And otherwise, thank you guys, and we'll see you guys in about 2 weeks. We'll be talking some more.
Great. Thanks. Thank you. All right.
All right. I think